Hello GMAT Club. Let's talk a little bit of data sufficiency here. And there are two clues. Data sufficiency is kind of a game unto itself. At Veritas Prep, we like to say, think like the test maker. Why are they writing things the way they are? Why did they add that word? Why did they phrase it that way? Those kinds of things. The test maker sometimes is setting traps for you, but other times they're leaving clues. And if you can train yourself to recognize these clues and leverage them and use them, you can be way more efficient. Get more problems right, use your time more wisely. We'll talk about even guess right. If you don't really have the right to get that question right, you kind of know where it's going. If you leverage these clues, you can be way more effective at data sufficiency, and there are two clues that you're probably not using very much at all. And so we want to talk about those. One is the combination question. This is one of my all-time favorites. Once you recognize this, you know how to spend your time, you know how to set up your math. Anytime they ask you for a combination of variables, there's something at play there. That should be a clue to you that you want to leverage assets, so to speak. You really want to get to work to try to solve directly for that combination instead of getting the individual parts and then combining them. We'll show you what we mean with an example there. And then the other one is if there's an obvious statement. Anytime one statement is dead obvious on data sufficiency, well, think about it. If statement 2 nobody would ever say is sufficient, there's no way anybody would ever pick B or D, well, then they've just made that problem a little bit easier. What does that mean then? Why would they throw away a statement like that? It's either to set a trap for someone, lay a little bit of a trap for people who aren't thinking critically, or it's there is a clue that other people can leverage. Something's going on with the other statement, and you want to make sure that you look at the obvious one and see, hey, what does that tell me I should be thinking about? So let's take a look at this first one with sort of an all-time classic question here. What we've got going on is that if triangles A, B, C, and C, D, E, and they picture those for you, are each equilateral, they want to know what is the sum of the perimeters of the two triangles. And this is pretty important here. Look, it's a combination they're asking for. They're not asking for one side or the perimeter of one triangle. They're asking you for an overall combination, the sum of the two perimeters. Well, I want to show you the statistics. Before I do, if you want to try it for yourself, feel free to pause the video, give a quick half beat there for you to do that. If you look at the statistics, you'll see the mistake everybody's making here, not everybody, most people here, and you'll also see how to avoid that. People go hard for C on this one. They think you need both statements together. I'll show you why. The right answer is A, and to me, as soon as I see that they're asking me for that combination, I'm ready to try to do more with less information. I want a more sufficient answer than needing both of them or not being able to do it all with E. I want something extra sufficient, and here's why. The reason people pick C is they look at statement 1 and they say, okay, I know that this here is 25, but I don't know how that's broken up, so I can't get the perimeter of a small triangle, I can't get the perimeter of the big triangle, I have this one line, I'm close, but I can't do it. Then they see statement 2, and statement 2 might even kind of fit what we're going to talk about next. People should see, hey, statement 2 isn't going to be sufficient on its own. I need perimeters. All this gives me is a ratio. But people look at that and they say, oh, I see what's going on. It breaks it down in a 2-to-3 ratio. So this is 10, this is 15. They're equilateral. I can do it all. But look at what people are using when they pick C. They get the perimeter of a small one, 10, 10, and 10, so it's 30. They get the perimeter of the big one, 15, 15, and 15, so it's 45. Then they combine them. If they ask you a combination question, the big hint is they almost always make it easier with less information to solve directly for the combination instead of getting the individual components, perimeter of a small, perimeter of the big, and then combining. So how do we do that? Well, here's where you need to leverage assets. That combination question to me always means, hey, I need to really leverage my assets. I need to do some work. And so maybe what I'll do, some of the perimeters, let me even just see what that's going to look like. I'm going to say label these X, X, and X, y, y, and y, and just say, okay, I'm going to label my diagram. I'm going to work a little bit. What do I need to get the sum of the perimeters? It's 3x plus 3y is the sum of the perimeters. So you might not need to label. You just say, okay, I need 3 small sides plus 3 big sides. And you can think that through in your head. Either way, you want to really look at how do I get the most out of the least information, because they asked me for a combination. Well, now you're probably, what does statement 1 tell you? It tells you 1 small side plus 1 big side is 25, or x plus y is 25. Well, if I triple that, I get 3x plus 3y. Or if I work on this one, factor out the 3 and say they're asking me for 3 times x plus y. Well, if x plus y is 25, 3 times that is 75. The math isn't insanely hard on this. What is difficult, again, as you look at the statistics here, way more people fall for the trap C on this one than pick A. What's difficult is the way you tend to do math. The way most of us were taught for math is solve for x. Oh, they want me to combine it with y. Okay, solve for y. Now add them together. When you get to a combination question on data sufficiency, that's a clue to you that, hey, there's probably a more efficient way to solve directly for the combination with less information, with only one statement, maybe each statement alone. There's a way to get to it with less information than it would take to solve for the individual variables and then combine. So if they ask you, what is x minus y? What is the sum of the 2 perimeters? What is the difference in the ages of these 2 people? Whatever combination they ask you, know this. I've always loved the Rolling Stones quote for this one. You can't always get what you want. What you want is, I want the small perimeter, I want the big perimeter, and then I'll add them myself. You can't always get what you want. But if you try sometimes, and I think this is really important, you got to roll up your sleeves. You got to label the diagram. You've got to do some algebra. You've really got to think through, this is the combination I need. How am I going to factor or otherwise use my math to get to this combination? You can't always get what you want. But if you try sometimes, you put in the work, you might just find you get what you need. That's what combination questions on data sufficiency are all about. So once you see that clue, which I'll be honest, I was teaching this test for a few years before I started to see that for myself. Once you see that clue, you know where to spend your time. And you also know that, hey, if it's an adaptive test and I should be doing well and I'm running a little low on time, hey, it's obvious you can do it with both statements together, but it's a combination question. That also tells you you've got pretty good odds if it's supposed to be a hard problem, and that's a clue that's easily overlooked. Maybe you guess the harder answer choice there, the more sufficient answer choice there. If you have the time, that means you roll up your sleeves and get to work. If you pick up on that clue, you've got a competitive advantage on data sufficiency. Now let's take a look at one more. We're going to talk about the obvious statement. What do I mean by an obvious statement? Take a look at this question here. What is the value of integer z? And then look at statement 2, y is not a prime number. If you're not looking at statement 1, you're just looking at, no one in their right mind would ever say statement 2 is sufficient on its own. They asked you about z, all they told you about is y. There's no reason you would ever pick that. When one statement is obvious, it's either a trap or it's a clue, but it tells you something you better be thinking about with the other statement. And so give you guys an opportunity. If you want to pause the video and try on your own, give it a shot. I'll wait a second or two here. Let me show you guys the statistics on this one, because this is another one where the statistics, these all come from the Veritas Prep practice test. They show you, hey, people make this mistake a lot. People very often pick A when the right answer is C. Of course, what's more interesting is why do people pick A and what should you notice about C? Here's what's going on here. People look at statement 1, you kind of have to pick numbers because it's way too abstract, I think, for most people to try to think about conceptually or to set up some algebra. We've got z as the remainder when positive integer y is divided by positive integer y minus 1. Okay, it's a lot to think about. Y and y minus 1, adjacent integers, consecutive integers. So you go, okay, what if y equals and y minus 1 equals? What if y is 5 and y minus 1 is 4? Well, then the answer is 1 remainder 1. So, okay, I see z is the remainder, it could be 1. All right, that's only 1. Let me try something else. Let me just say, okay, y is 10 and y minus 1 is 9. All right, if I divide those, I get the same thing, 1 remainder 1. Maybe you try bigger numbers, 100 divided by 99 or 1,000 divided by 999. You kind of keep getting to 1 remainder 1. And so very often, the way you're trained to do it very often on basic data sufficiency prep videos is make your decision on statement 1 and then forget all about it. You don't even want to think about it. It's either AD or it's BCE. Then look at 2, and if statement 2 is not sufficient, cool, it's A and move on with it. If one statement's dead obvious, you may want to look at that one and go, okay, wait a second. What didn't I think about here? Why is not a prime number? Why would prime versus not prime matter? Maybe you try 3 divided by 2. No, that's not quite it. What's the weird prime number? The lowest prime number, the only even prime number. Hey, wait a second. What about 2? Would 2 change things? If you try that one, 2 divided by 1 is 2, remainder 0. That's your only spot where it's different. That's where you get a different answer to show that statement 1's not sufficient. And I'd say you really have 2 chances to save yourself here. One is to take the hint from here. Okay, wait a second. Statement 1, I got my thing. They threw away statement 2. So I better consider prime versus not prime. And as I'm doing that, what kind of unique prime numbers come up? If you ever see prime as a definition in data sufficiency, you should think about 2 because it's the weird prime number. All the others are odd. All the others are bigger. 2's the weird one. At least give it a passing glance and see why it might work. The other one is if you're ever picking numbers, you've got to try to play to the edge cases. What's the smallest number they'll let me pick? What's the biggest number they'll let me pick? What about negatives? What about fractions? Here, when they say you've got 2 consecutive positive integers, the lowest you can go is 2 and 1. 0 is not positive, so 1's the lowest positive integer. If you're not trying the edge case here, what are you doing there? You're making mistakes. You've got to play to the edges. If you just try 5 and 4, 6 and 5, they're the same number on the number line. You want to try to play to the edges. You got 2 chances to save yourself here. And again, if you look at the statistics, people don't take it. More people pick A than pick C. Way more than half of people get this one wrong. If you recognize a dead obvious statement is either a trap or it's a clue, but it gives you some insight into, hey, before I finalized my decision on statement 1, statement 2 was pretty useless. It told me to consider prime versus not prime. Why might I need that information? That's what it's telling you. So yeah, in general data sufficiency, theology, I guess, or theory, make your decision on statement 1, then forget about it so you don't carry over information. Then make your statement on statement 2. But if one of those 2 statements is dead obvious, you want to at least kind of hold it up there and say, okay, what might this be telling me? I'm not going to use it, but if they said prime or not prime might matter on statement 1, I better go back and say, what would make things a little bit different there? And so that's a clue you really have to use. When one statement's dead easy, it's a clue or it's a trap. You just have to ask, why is it there? Why might it matter? Sometimes you go, no, that doesn't matter, and here's why. Other times you look at it and you go, oh, wait a second, yeah, this clues me into a number combination I should have tried or something else. Now also, some clues yell at you. If statement 2 is useless but it says y is positive, well then it's, hey, did you consider positive negative in that inequality in statement 1? Others whisper it. Others might say it's greater than 3. This one whispers, hey, it's also positive. They throw you off the scent a little bit. Same thing before. It wasn't that all prime numbers would give you one answer and all non-primes would give you another. They were whispering, you better think about 2. And so you want to make sure you're kind of heeding the clue. An easy question, they yell the hint, or a moderate question probably, they yell the hint. On a harder question, they whisper it a little bit, and you kind of have to, hey, why might that matter? Okay, if it's greater than 3, that means it's greater than 0. Did I consider what negative numbers would have done before, or something like that? So make sure you're asking yourself, when you get a dead obvious statement, are they whispering at me? Kind of think of why that might be there. If you just ask yourself the question, hey, why are you here? You're in good shape with that clue. And so let's summarize those 2 clues that you're probably not thinking about nearly enough. If it's a combination question, that means you want to try to solve directly for the combination. If there's one obvious statement, sometimes it's dead obvious insufficient, other times it's dead obvious sufficient. But if no one's really putting any thought into one statement, it's either a clue, it's a trap, and it's up to you to figure out why it's doing there. Well, what does that do? Here you can see it helps save us from mistakes. The 2 most popular answers answers to each of those questions was a trap. If you were heeding these clues, it saves yourself from that mistake. 2, it determines where and how to spend your time. If you know it's a combination question, you want to roll up your sleeves and do some algebra, or try to solve directly for that combination. Label all your diagram or something like that, because you know, hey, there's a clue there. Usually when they do this, there's a reward for those who are willing to do the work. That you can't always get what you want, but if you try sometimes, you might just find you get what you need. And then also, this is kind of important too. Hey, it's a time test. Pacing is difficult. It's also an adaptive test. If you're at question 24 on the quant section and it's data sufficiency, and there's a pretty obvious answer you want to pick of like, oh, you can totally do it, but they ask me for a combination, you may want to guess with better than random probability. If it's easy to get C, like that triangle problem, and hard to get A, you might want to say, hey, I could spend my time here, but I don't know that I have the time to invest. If I'm doing well on this section, if it's late in the section and I should be doing well on an adaptive test, and it's a combination question, and it's pretty easy to do it with both pieces of information, I bet you can do it with only one. I bet it's either experimental and it's easy, or it's hard and you've got to leverage some information. You can get pretty good at giving yourself a better than 50-50 chance on some of these just by kind of reading that intent. If you know what that clue is telling you, you know either where to spend your time if you have it, or how to blow in a pretty high probability guess if you don't have the time. So to summarize, recognize these are 2 clues you better look out for now. Obviously, in practice, you can get a little bit more comfortable with those, but look out for these clues. Data sufficiency is a math question. It's also a logic game. If you understand your opponent, the test maker, or what kind of clues they're leaving for you, you've got a much better chance at getting questions right.